bring somebody down if I never made a sound again. In your eyes, you've already spent my thighs, and you're rocking to the next big thing. Kissing the bride, 45 minutes aside. This was my dream, played out rockin' routine. Who sucked out the feeling? Who sucked out the feeling? Where'd you go now that everybody knows that we did a couple shows out there? Look at me, I can write a melody, but I can't expect a soul to care. Kissing the bride, 45 minutes aside. This was my dream, played out rockin' routine. Who sucked out the feeling? 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 Kissing the bride, 45 minutes aside. This was my dream, played out rockin' routine. Who sucked out the feeling? 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 Who sucked out the
All right, so today we're going to be starting on what is labeled as Module 7. You'll be working through Module 6 through this week. That covers the rest of functions, including pointers, pass by reference, and formal unit testing. And then, of course, your reading for next week will be on arrays, so we're going to go ahead and start those this week. You do have a midterm coming up in a couple of weeks, I believe, and that will cover everything up to and including arrays. So everything that we've been doing over the last couple of weeks, functions, pass by reference, pointers, and arrays will be on that midterm. Pretty much the same format is what I'm planning currently as the first exam, but it is worth, I believe, 100 points instead of the usual 50. All right? All right, so what are arrays? Well, arrays are collections of things, right? In programming, it's very, very rare that you're actually going to deal with just one variable or one piece of data or one number. Instead, you want to be able to process a collection of pieces of data, right? So if you're modeling students or grades or something like that, you don't have just one grade, you have an entire class of grades, right? If you're trying to model whatever you're trying to model, you're probably going to have more than one if you want it to be a useful program. In C, collections of similar pieces of data are stored in arrays. Right? And note here that I'm going to, I don't think, is there an underline and markdown? Yep, well, okay, that's an emphasis. Similar pieces of data. In other words, when you create a collection, that collection is only going to be a collection of integers, or it's a collection of doubles, or it's a collection of whatever you're trying to model. It can't be a collection where you've got a mixed kind of type, where you've got a couple of integers and a couple of doubles and a couple of whatever else you have in there. It all has to be of the same type. There are programming languages that support arrays or collections of what are called mixed types, but that's not really supported in C, or at least we won't be doing it, right? So what are arrays? Arrays are ordered collections of variables of the same type. Right? In other words, again, integers or double, etc. Right? Arrays have an identifier, a name. Right? Again, the formal term for that is identifier, right? But we'll just call it a name. Right? Elements in an array can be accessed using an index. So an index, we've seen this before. We've seen this term before, at least, in the context of, say, an index variable or an iterator variable is sometimes what I called it. But an index, or the number of command line arguments, right? When you use argv, the first one is at index 0. That's always going to be the executable file name. The first actual argument that's provided by the user is at 1. The second one is at 2, et cetera, et cetera. That's what the index is. Indices start at 0, right? And are all contiguous integers. In other words, they go one after the other. So in other words, if you have an array of integers named ARR, then the first element is at ARR sub 0. Right? The second is at ARR sub 1. Where's the third? The third is at ARR of 2, etc. Right? You can index using a variable. So, for example, you can say the ith element, ARR sub I, is the ith element. The last element, assuming there are n elements, or the size is n, or the cardinality, or whatever you want to call it, is at ... So if there are n elements in there, then where's the last one? Remember, we're starting at 0. We're not starting at 1. If we were starting at 1 and there were 5 things in there, it would be 1, 2, 3, 4, 5. But since we're starting at 0, it's going to be 0, 1, 2, 3, 4. In other words, 1 less. So in general, if I've got n elements, where's the last one? Is that n minus 1? There we go. Okay. So let's just go ahead and get into it here with C. Right? We're going to start with something that's easy to work with, at least initially, something called static arrays. Static arrays are arrays that are of a fixed size and allocated on the program stack. Okay. Remember that what the program stack is. If you've got a function calling function, calling function, calling function, you've got stack frames that are allocated on top of each other, so that it's highly organized, right? It's a highly organized stack that you're in the current function here, and you're about to return. What do? You pop off that stack frame, and you're automatically back at the function that you started at, right? It's a bunch of breadcrumbs. As function calls function calls function, you're adding stuff on top of the stack frame. With a static array, that array will be in a stack frame somewhere, right? So let's go ahead and go over here and demo how to do this, right? I'm going to go ahead and just keep it simple. Let's go ahead and go with an integer array. Oops. Not reset, but go back. There we go. An integer array. If I just did int x, that declares 1 integer. I want to declare an integer array that can hold 5 integers. So I'll call it ARR, short for array. If you want to call it array, fine, but I'm just going to go ahead and go with ARR here. And I'm going to specify that there are 5 elements in it. Note there that I'm using the square bracket syntax. The same square bracket syntax that we use to actually access each individual element. So if I've got 5 elements in here, then I can set each one of them. ARR sub 0 is equal to 42. I'll set the first one to equal to 42. ARR sub 1, that's the second element. I'll set that equal to 101. Oops, too many. There we go. I won't bother setting this, the third and the fourth element, but let's go ahead and set the last element here to 129. Is that correct? Is that the last element? Nope. So just an informal poll here. Over the weekend, I had to review the CSAP exam. That's the Advanced Placement exam. And in it, they used 1 indexing. What we're using here is 0 indexing. The vast majority of programming languages will use this, and we'll understand why later on when we learn how this stuff works in memory. But there are programming languages that do things slightly different for weird reasons. 2 of them that you might have heard of. One of them is Scratch. How many people use Scratch in high school? Okay. It started at 1. It is very non-standard. I think it's because it was aimed at a younger audience, and so younger audiences don't intuitively start their counting at 0. They intuitively start their counting at 1. The other one that I'm thinking of is, has anybody had ever done any like Roblox programming? All right. So what language do you use in Roblox? Lua, L-U-A, Lua, and they do indexing at 1. Those are the only 2 languages that I imagine anybody in here has any idea about that exist that have ever done that. There are a couple dozen others that nobody has, that are not, hugely popular or anything. And despite that, the AP exam still used 1 indexing. And I wrote on my review, if you're going to do this, like this is extremely biased towards Scratch, people who had Scratch as their AP class, which is probably a minority. If you're going to do it, like the vast majority of them are probably going to either use Python or Java, and neither one of those uses 1 indexing. We use 1 indexing here. So I was just curious to see how many people had actually seen either one of those programming languages that does something completely different. The other one that some of you might know is MATLAB, which is a general engineering programming language. All right, so the last one is at 4 because we have 5 elements and we start at 0. Okay, let's go ahead and let's go ahead and print these. Right, you can iterate over the elements in an array using an idiomatic for loop. Idiomatic, right? For int I equals 0, I is less than something, I plus plus, right? The usual stuff that you just start writing without even really thinking about it once you get into it. While I started at I is equal to 0, I is less than 5. Why less than 5? Because it'll go up to 4, but will it include 5? Nope. So that's why it's idiomatic. You go up to, but not including the last element, I plus plus. And now we understand maybe why we use I. Why do we use I? What is it standing for? Index, exactly. Right? And then let's go ahead and print it out. Printf, ARR sub %d is equal to %d, end the line. Right? And I'll print out the index, and I'll print out the thing stored at that index. Okay? GCC, demo, and this is just simply going to print out 42, 101, ooh, what about those other 2? And then finally, 129. What is it going to print out for ARR sub 2 and ARR sub 3? What would you guess? It could be garbage. 99% of the time, it's probably going to be 0. But that's the point that I'm trying to get across. If I just create int x, what value is stored in x at that point? 0, most likely, but sometimes garbage, sometimes dead beef, sometimes whatever was there beforehand. Now, in this case, it's probably going to be zeros. Right? Well, it's not always the case. I'm going to pump this up to 5,000 elements. Pump this up to 5,000 elements. If indeed it was always 0, we should only ever see 0 everywhere. And I can almost guarantee that we ain't. Lots of zeros. But at some point, we get what? Something. Garbage, 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 garbage. There's a bunch of zeros. Garbage, 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 garbage. Right? So do not think that there are default values that are loaded up into an array in C. Right? Whatever garbage happened to be there beforehand is probably what's in there. Okay? So, careful. C has no default values for elements in an array. Could be 0, could be 0, could be garbage. If you have an assumption on what is in your array, you need to make sure that you write code to enforce that assumption. Okay? Let's go ahead and take this and bring it over here to, oops, just in here, to this Python visualizer. Because I just simply want to show you what it looks like. Right? Remember, this is a static array. Now, we've heard the term static before. Static analyzers versus dynamic analyzers. A static analyzer, like the wall flag, a linter, that looks at your code before it even compiles. Right? In other words, your code is there, it's static, it is what it is. Right? It's not moving. And it looks at your code and says, well, that looks fishy, that looks fishy. You might want to take a second look at that. A dynamic analyzer like Valgrind that we previewed on Friday, that looks at your code as it's running, as it's moving, as it's doing things and changing things. That's a dynamic analyzer. Static here is a different context. It means that it was allocated on the heap. Take a look at that. Main, that is a stack frame. That is a function call frame. And that's where the array is stored. Right? We set 42, 101, 29, 129, etc. And then we go ahead and print them out. It's really emphasizing here what the third and fourth element are. What are they? Question mark, right? Who knows? I wonder what happens if we actually print these out. 42, 101, oops, conditional, ooh, there we go. Uninitialized value. So at least in this simulation here, in this visualizer, it dies out on it, right? It didn't die out on us in VS Code over there because that was probably the system stepping in and providing a 0 value. It's actually dying over here. That's kind of weird. I wouldn't have expected that to just absolutely die. In any case, it can't go any further here. But the thing that I want you to note here is that it's in a stack frame, and it's all contiguous. We've got the first one, the second one, the third one, the fourth one right after the other. In other words, if we were to look at this in terms of memory, it's all one contiguous chunk of memory. They're all together. There are no gaps, okay? Let's come over here and look and see what happens if I try to increase this up to not 5,000, but 1, 2, 3, 1, 2, 3. We call them what? Millions, all right? I don't want to print it out, though. There we go. In fact, I won't print it out. I'll set the last one here. Set the, oops, comment. Set the last value to, I don't know, -1. No, let's go with 10. ARR sub, where's the last element now if I've got 5 million elements? 4,999,999. There we go. Is that right? No, one more? Ah, screw it. What's a better way of doing that? 5 million minus 1. There we go. All right. Set that equal to 10. Because I don't know if I'm mashing my keyboard correctly or not. All right. Now, let's think about this before it runs. All right. It's going to compile just fine. In fact, it's going to compile even with the wall flag. It's going to warn me that you're not actually doing anything with it, but that's an irrelevant warning here. All right. So it compiles with no relevant warnings, okay? Let's think about this before we run it. Remember that stack space, right? The stack of dishes doesn't go too high, right? If you stack 500 dishes in the cafeteria, is it likely to be stable? Probably not. It's going to fall over. Likewise, the system stack isn't that big. I can tell you how big it is. Running a utility called ulimit, that's short for user limit. Tell me about everything, okay? So let me come up here. For example, file size, you can create an unlimited file size. Right? Maximum memory size, it's unlimited. In other words, if it has more memory to give, it'll just give you more memory, more memory, more memory. But if I look down here at the relevant part, stack size, it's limited in terms of kilobytes here. 8,192 kilobytes. That translates to roughly 8 megabytes, all right? So we have a limit of 8 megabytes on our stack. The dishes only go so high. They only go up to 8 megabytes. What am I attempting to do here? 5 million integers. Tell me, how many bytes does an integer take? 4. So 4 times 5 million is 20 million. 20 million bytes. Is that more than 8 megabytes? Yep, that's nearly 20 megs. So let's find out if we can stack the dishes that high. There we go. Segmentation fault. Nope. I'm not even going to bother to put that over here into the visualizer because I will have something that is 5 million things long, right? Or if you put it up properly, like a stack of dishes, you've got 5 million dishes in your stack. Too big. If your stack grows too big, what happens? It'll fall over. We call that what? Think of it like a a bottle of water or a cup of water. You keep filling it, keep filling it. Now it's full. What happens if you put in more water? Overflow. Kind of a, stack overflow. Right. Sound familiar? Right. Stack overflow, where developers learn, right? Learn not to overflow their stack, for one, right? They learn that really quickly that a stack is limited. In fact, this is quite large, right? If you were in an embedded system, or if you were in a system with fewer resources, or if you were in an older system, certainly, you would not even have 8 megabytes to spare. You might have 1 megabyte. You might measure your stack space in terms of kilobytes, right? This is not going to be something that we're going to do for very long, right? We can't even fit a reasonable amount of data, even just 5 million integers over here, right? Okay, so observations from doing all this stuff. Right? Actually, let me go ahead and make sure that undo. Let's go back, and let's make this only 5, and let's make this only 5, and there. I'll make sure that you have this syntax in your notes. There we go. Our observations were, let me make sure that you've got this first before we start making our observations. All right, there we go. Observations, right? There is no default value for array elements, right? It could be 0. It could be garbage or dead beef, right? Etc. Right? What else did we do? No default values. Static arrays are allocated the call stack, which is limited in size. Right? Say, for example, 8 megabytes. Right? You cannot create even moderately large arrays on the system stack. You need a different solution, ... That's where we'll go next. Another observation here. Attempts to access invalid indices are undefined behavior. Right? So, for example, let me come back over here to our array. And what if I were to try accessing the following? What if I were to try to access the negative first element and set that equal to 101? If we start our indexing at 0, does that make any sense? Let me go back over here to the visualization. Right? If I treat this as just like a tabletop, right, where it starts at one end at 0 and goes all the way to 4. If I try to access the negative 1th element, right, I'm going this way. Does that thing exist? Nope. So what happens? You fall off the edge of the table. If you try to access the 6th element at index 5, likewise, you fall off the other end of the table. Right? That is undefined behavior. Right? That, you're not going to be able to do that and expect anything other than garbage results. You should not access elements larger than the array. For example, array sub 5 equals 101. Right? If I try to access that last element thinking that I'm in Scratch or Lua and that we're starting on 1 indexing, that's also undefined behavior. Now, let's go ahead and try to compile this. In fact, it's going to compile with no warnings at all, probably. Right? Perfectly fine. Go ahead and do whatever you want. It's your memory. You can screw it up as much as you want. That's the philosophy here. Right? Let's go ahead and try to run this. I am 99% sure that it will run without any issues. Right? So it must work. Maybe we can do this. Right? Can we? Nope. Let's use that tool that we just learned on Friday to see if there was any error that simply did not manifest itself as a segmentation fault. There can be errors that are silent, right? Those are the worst kind of errors because you never see them manifest as that something's going wrong here. Remember Valgrind? Right? In fact, let me go ahead and compile this. What flag did we use on Friday to ensure that we kept all of the line numbers, all the variable names, et cetera, et cetera. Hyphen G. Right, there we go. Good. Now let's go ahead and run it through Valgrind. Valgrind, run a.out for me, and give me a report of anything bad or illegal or undefined that I do. Were there any errors? Well, it output without any errors. Ooh. How many errors were there? 10. I did a lot of bad things. All right. What are those bad things that I did? Well, mostly on line 13 and 14 here. Right. In fact, if I go up to the top of the report and start out, let's see, where is it? Invalid read at line 24. Line 24 is me printing stuff out here. I didn't do anything illegal on that line, did I? There were 5 elements in that array, and I read and printed 5 elements. My real mistake up here was corrupting my own memory before I got to that point. Right? I've screwed up my own memory here. Right? After this point, there is no recovering from that internally. That's why it's complaining about it down here on line 24. You've already corrupted this array. We've already screwed up this array on lines 17 and 19. And then down here, it's reporting those as errors when we actually try to print anything out from that array. It's already corrupted. Every single read or write to this array after that point is going to be undefined behavior, is going to be a bunch of errors. Right? So even though we didn't see it, yes, keep working. Even though we didn't see it like end with a bad segmentation fault or anything, that doesn't mean that everything was good. Right? Valgrind is really the only tool that you can use to make sure that everything is going good, and to try to find out where things went bad if they did. Okay. All right. So those are our observations. Attempts to access invalid indices are undefined behavior. Example: if you try to go array sub -1 or array sub say 5. If size is 5, right? They're all bad. Let me show you how I can maybe hopefully force a segment. Oh, yeah, go ahead. Is there a question? No? Oh, okay, sorry. Anyway, let me go ahead and try to force a segmentation fault here. If I go 1, 2, 3, 1, 2, 3, 1, oh, that's just big, right? If I go ahead and try to access memory that certainly does not belong to me, right? Something way beyond the scope of my own stack frame. Hopefully it will now be a segmentation fault, right? I jumped so far away from that small table of 5 elements, right? I jumped so far away that I got into somebody else's memory. It was fine as long as I stayed close and only screwed up my own memory. The operating system is perfectly fine letting you screw up your own memory as much as you want. But the second that you get so far away from your own memory that you're now mucking up with other people's memory, right, other processes' memory, that's when the operating system steps in and says, no, you can't do that. Right? Ending with the segmentation fault here. Is that 50 million away? Right? That's how I was able to, you could also go negative 50 million, right, and get the same result here, hopefully. Yeah, segmentation fault. Right? Okay. So, it's too small, right? Static arrays can only hold at most 8 megabytes. Right? So what's the solution here? Better solution are dynamic arrays. Right? So to store even moderately large data, you need dynamic arrays. Dynamic arrays are arrays whose memory is allocated on the heap. Right? So we've got 2 notions of piles of stuff at this point. The analogy that I use with respect to the stack is this highly organized plate on plate on plate on plate, right? That a stack frame after stack frame after stack frame, you only have a limited access to that, right? And every time that you call a function, a new stack frame is created. It's pushed on top of the stack. Anytime that you return from a function, that stack frame is popped off the top. Highly, highly organized. Think about those dishes in the cafeteria. Highly organized. You know where the first dish is, you know where the second dish is, you know where the third dish is. What do you think when I say heap? A heap of stuff. What immediately comes to mind? Oh, the plates fell over and all broke and everything. Think of something a little bit less breakable. Well, if you're anything like me, where do you throw your dirty clothes? In a pile, in a heap, right? So if you've got a heap of clothes there, you throw something on the top, maybe it stays there, maybe it doesn't. Maybe it falls down in the middle of the heap. Maybe it falls all the way down to the ground so that you can start building up a larger heap and larger heap, right? That's what I think of when I think of a heap, or a heap of garbage, right? A heap is much bigger but less organized, right? In general, the heap is less organized, but much, much larger than a stack. So in other words, that 5 million integers, which is 20 megabytes, that's nothing to the heap, right? The heap is much larger. The heap is unlimited. It's only limited by the amount of memory that your computer has or that your computer supports. So you can allocate much larger pieces of data on the heap. It's a little bit less organized, and so you pay a price for that. You're never going to see that price paid manifest itself with C or anything that we're going to do in this class. So don't worry about it, but it is a little bit less organized. But it means that we have to do our own bookkeeping, right? For all types of arrays, but especially dynamic arrays, you need to do your own bookkeeping. What that means is, to create an array, you need to allocate new memory to store it, right? By making a request to the operating system. When you are done with it, when you're done using that memory, you need to give it back or free it up, right? This is known as memory management. This is the price that we pay in C for low-level access, where we can actually grab access to memory. Other programming languages, like say Java, Python, those are memory-managed programming languages. That the programming language or the virtual machine that you're running on handles all those small, low-level details for you. And it comes at a price. It is not trivial to manage memory, right? You're putting all that on the Python interpreter or the Java virtual machine or whatever you're running, right? You pay a price for that in terms of efficiency. The price that you pay here for an increase in efficiency is an increase in your own responsibility. Again, with great power comes great responsibility. If you allocate 50 megabytes of data, once you are done using it, you need to give it back. If you don't give it back, bad things happen, right? Now, it's not like you steal memory out of the computer and then the RAM gets up and walks away or something like that. You're not destroying memory. It's just that you're hoarding memory. If you grab a bunch of memory and never give it back and your program keeps running, guess what? If you keep doing that, grab 50 megabytes, never give it back, never give it back, never give it back, and your program is a long-running process. That's called a memory leak. Eventually, you will run out of memory, or even if you don't run out of memory, long before you run out of memory, your system performance goes down, 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 down. Right? It used to be that I'm using Firefox over here. It used to be that Firefox was notorious for memory leaks, because this is a long-running process. People typically have a web browser open for hours on end. Right? If every few minutes it's grabbing a huge chunk of memory and not giving it back, not recycling it, eventually, if it's running for hours and hours and hours, right, then the system grinds to a halt because Firefox has taken way too much memory. That was many, many, many years ago that it was notorious for that. They've pretty much fixed it up. And everybody should be migrating back to Firefox as soon as possible before Google shuts off all of the ad block stuff, right? So if you're interested in what ad block software I use, Privacy Badger, Ghosterly, DuckDuckGo Privacy Essentials, and AdBlocker Ultimate, right? I haven't seen an ad in years, right? So you shouldn't either, right? But that's not going to be possible with Google Chrome or Edge or anything Chromium-based going forward, right? All right, so that's known as memory management. So how do we do this? How do we do this? So to allocate memory, you use the memory. How's that? Yeah, that's looking good. Allocation function. There we go. Yep, that looks better on the screen there. Memory allocation function. I highlighted those words, M and alloc, because that's the name of the function. Malloc. And it stands for memory allocation. Okay? It has the following signature. And let me go ahead and just grab this. Some new syntax, or familiar syntax here, but we have to explain it. So first of all, what is size t? Size t can be treated as an integer, right? You are basically ask malloc for a certain number of bytes, right? Indicated by size, right? So that's the input to the malloc function. How many bytes do you want? Well, for this one over here, if I wanted 5 million bytes, right? Int n is equal to 5 million. That was not possible before, so let me go ahead and get rid of all that code there. That was not possible before. But now it might be possible calling malloc. Right? How many bytes do you need for 5 million integers? So how many bytes for each integer again? Yeah, 4 bytes per integer, so 4 times 5 million is 20 million. 2, 0, 0, 0, I don't know how many zeros there are. Don't do it that way, right? Let the compiler do it for you, right? First of all, to do this properly, use size of and an integer to keep track of the number of elements in your array. Right. So let's talk about each one of those in turn. Always keep track of the size of an array in an integer variable. Say n. That's what I'm doing in the example here. And here I want, how many do you want? I want 5 million. Put that into a variable. The second part is the size of. So how many bytes does an integer take again? You already told me, 4. How many bytes does a double take? 8, typically. Right? But here's a dirty little secret of C. How many bytes does an integer take? According to the C standard, only at least 2. Right? It could be 3. It could be 4. It could be more. Right? The C standard doesn't say anything other than it has to be at least 2. So to make your code interoperable, what you can do is you can use the size of, it's a macro that's defined in the standard library. So you can get how many bytes each type takes using size of. Right? So for example, size of int. Right? That will resolve to 4 on most systems. On systems where it's only 2, or weird systems, and there are systems like this, old and out of date, probably unused, there are some systems where it ends up being 3, really weird. Right? And you can use size of double. Right? You can use size of char. Any type that you have, you can put that into size of, and it'll effectively return. It's not really a function, but you can treat it like a function. You can think of it like a function. It'll return 4 for an integer, 8 for a double, 1 for a character. Right? Always use size of. So how many bytes do you want over here if you want 5 million integers? Simply just say, I want n of them, and each one of them takes size of int bytes. Right? That's how many bytes I want. Give me that many bytes. Now let's focus on the other part here. It returns this weird thing right here. This weird thing called a void pointer. Right? So what is that? Right? Malloc, am I back out? There we go. Malloc returns a generic void pointer, right? A void star. So we've seen these before. It's just that we haven't seen the void pointer before. Int star is a pointer to on. Tell me all about that. What is it pointing to? A memory location of an integer. I like that even better. A memory location that holds, or is supposed to hold, an int. Right? What about double star? What is that? It's a pointer that points to a memory location that holds a what? A double. Right? So, what is void star? What we've done is we've erased the type. Right? So if a function returns an integer, it's an int function. If a function returns a double, it's a double function. If a function returns void, it doesn't return anything. In this context, though, it means something a little bit different. Void star is a pointer that can point to anything and everything. No, I'll leave it like that. Anything. I don't want to say everything. Right? That'll give the misimpression that it's pointing everywhere. Right? It's not. It's pointing to a raw memory location. It is pointing to a raw memory location that can hold anything. Int, double, etc. It's just a memory location. Malloc doesn't care what you're going to use this for. I want 20 million bytes. Okay, here you go. Right? Have fun. Oh, by the way, Malloc, I'm going to use that 20 million bytes to store 5 million integers. I don't care. Do it. It's your memory now. Do whatever you want. Or I'm going to use that 20 million bytes to store 2.5 million doubles. Again, I don't care. Right? It's your memory. You asked me for memory. I gave it to you. Right? So to deal with this, we typically typecast the returned pointer to the type of variable we want to store. So let me come back over here and do that. I want to store a bunch of integers. So I want to force that void pointer to become an integer pointer. An integer pointer is int star, ARR. And I will make a call to malloc. But malloc, remember, returns this void star pointer. I don't want it to become a void star pointer. I want it to become a int star pointer. So all I need to do is, much like when you divide an integer by an integer, you need to typecast one of them, double, to force it to become a double so that you don't have 10 divided by 20 is 0. 10 as a double, 10.0 divided by 20, that is going to be 0.5. And so I'm going to typecast this as an integer pointer. After this, now you can treat ARR as a regular old array. ... For example, I can set the first one equal to 42. I can set the last one, which is at n minus 1, equal to 101. This won't crash. When I compile this and I run it, I'm not going to print them all out. I'm not going to print out 5 million things. When I run it, no segmentation fault. Whereas before, I tried to allocate 5 million, 20 megabytes, just short of 20 megabytes, on the stack, too many dishes. Well, it's okay. Use the heap over there. It's much, much larger. It's unlimited in size. 20 megabytes, that's nothing for the heap. Right? Go ahead. There's your 20 megabytes over there. Generic void pointer. Forced to become an integer pointer so that I could treat them all as integers. And assign 42, assign 101, etc. Now the problem is, once you're done playing with your toys, what do you do with them? You clean up, right? You put them away. Once you are done using your memory, be sure to give it back. Once you're done you're reading your checked out books from the library, you check them back in so that other people can use them, right? You put your toys away so that other people can play with them, right? To do this, you free it up. Free up some memory so that everybody else can use it. And it's really simple. The function is called free. You free your array, and now that 20 megabytes has been, that 20 million bytes has been deallocated and given back to the operating system. The operating system is probably holding that in reserve and will give it back to you if you make another request to malloc, but not necessarily. It could make it available for other processes. It could make it available for your process if you ask for it again. Right? It can make it available, just hold it for itself, and the operating system is now hoarding memory, right? But if you don't do this, there will be a memory leak, right? You will be wasting resources. Let me show you what that looks like as a preview here. Suppose I don't free them, right? In fact, suppose that I did this over and over and over and over again. We'll look at that in SQL here, right? Let me go ahead and just run this. I'm going to run this through valgrind. A.out. Actually, let me show you what a good run looks like. Valgrind A.out. Valgrind is going to simulate this and say, hey, everything looks good. Right? You allocated 20 megabytes or 20 million bytes. You freed it up. There are no errors. You didn't do anything illegal. You're all good. Right? If you do something bad, like, say, erase of, I don't know, 10 million, 1, 2, 3, 1, 2, 3, set that equal to 101. Let's try that. We already know what that should result in, right? A segmentation fault of some sort. Valgrind will report that. Valgrind will say, nope, you tried to, there's one error, there was a segmentation fault. Where did it occur? On line 10. When you, or not line 10, where is it? Up here. Line 14, there we go. An invalid write of size 4 on line 14. What is size 4 again? An integer. You tried to write an integer that doesn't exist. Okay, fine, I'll fix that, right? But now what happens if I don't free up my memory? There won't be a segmentation fault, because if you waste memory, that's on you, right? But if I run this through valgrind, it will say that there's one error. That error is now a memory leak. Let me come up here. Heap summary, where I was allocating it. In use at exit, 20 million bytes. That sounds familiar, right? A total heap size, there's one allocation of size 20 million bytes, and they were definitely lost as a result of your program. You now again, the RAM didn't stand up and walk away, right, out of the computer. It means that your program wasted 20 million bytes that it should have given back at some point. Right? What if I did this over and over and over and over again? What if I did this, say, I don't know, for int I equals 0, I is less than 1 million, there we go, I plus plus. All right. All I'm doing here is allocating memory, never giving it back because I'm not going to free it, and I do that 1 million times. 1 million times 20 million. What do we call them? 20 quadrillion? 20 quadrillion bytes. Right. GCC. Let's run this. Ah, finally, it was killed. Why was it killed? I had unlimited memory, right? Nope. I don't know. Let's find a name for this thing. What is it? What is 20? 1, 2, 3, 1, 2, 3 times 1 million. 1, 2, 3, 1, 2, 3 bytes to, I don't know, terabytes? Yeah, it's 20 terabytes. Right? How many people have a hard drive that's 20 terabytes on their laptop? Anybody? On their laptop? Really? No? Okay. So, it was unlimited, right? Well, no. You reached the limit at some point of physical, number of bytes, right? And so that's what we did there. Let me not go so much. Let me only go, I don't know, 10,000, right? Yeah, go ahead. Hard drive and memory, because once you filled up RAM, primary memory, then it goes to virtual memory. It starts writing whatever would be stored in RAM to disk, right? And then it becomes super slow because you're thrashing back and forth. That's why more RAM is better, but there ain't enough RAM in the world to do most computing processes. And so you have what's called virtual memory, where it's written to disk, and disk, like hard drive disk is what I'm talking about, is treated as memory. Anyway. All right. It got done really, really quick. I'm going to pump this back up to 1 million and see if I can run this. A.out, and then top. There it is. You see it? 80% of CPU. Oh, and then before it died, it was using 17% of all the memory available on that system there. And again, I don't know how much memory is there. It's not that much. If I were to do this on CSE, with only 3 minutes left, let's do this on our server here, the CSE server, because certainly it'll let me do this. It's got way more memory, and the limits are way less. So SSH There we go. All right. So I just cut and pasted a bunch of stuff. GCC foo. Right. So this is going to waste 20 terabytes on the CSE server here. Ah, segmentation fault already. Come on, really? I wasn't able to get away with it. GCC foo. Haha. I really wanted to do that. All right. No. I'll kick it down to 100,000. Come on. I can't run this on CSE. Oh, segmentation. I'm not doing anything. I'm not doing anything bad. All right. Anyway. Usually I would demonstrate HTOP. HTOP, there's all the processors on CSE. It's got 64 cores. Right? And you can watch them and see that here's the memory. It's got 126 gigabytes of main memory. Much more virtual memory here. And at any one time, only about a very small percentage of it is actually being used. And I definitely during your lab next week, we'll give you a buggy program like this, and you'll observe how much memory it actually takes, because we do slow it down so that it doesn't die right away, right? But you'll see this next week when you do your own experiments.